Welcome to another episode of Emerging Environments. Today on the podcast, we're speaking with Doctors Patrick Keys and Elizabeth Barnes of Colorado State University. Patrick is a lead research scientist in the School of Global Environmental Sustainability, and his work focuses on a broad range of global sustainability challenges, including climate change impacts, anthropocene risks, and social-ecological teleconnections. Pat is a true interdisciplinary scientist, and in our conversation, we talk about the rewards and challenges of interdisciplinary collaboration.
Elizabeth, or Libby, is an associate professor in the Department of Atmospheric Science. Her award-winning research focuses on large-scale atmospheric and climate dynamics, including jet stream dynamics, Arctic-midlatitude connections, and subseasonal-to-decadal prediction of weather and climate. She is also very excited about data science methods for the earth sciences, and her research group is developing a lot of innovative work in this area. Our conversation with Pat and Libby is primarily about a recent paper on the Human Footprint Index that they co-authored along with their collaborator, Neil Carter. A quick note about the conversation: Pat and Libby are collaborators, and they are also married. So the nature of our conversation definitely reflects these two dimensions of their relationship. So without further delay, let's get into the conversation.
Okay, hi Pat and Libby. Thanks so much for taking the time to join us on the podcast today. It's a pleasure to have you. We are excited to talk about this new paper you're both co-authors on related to the use of machine learning to examine a human footprint index. And we'll get into that in a lot of detail. But before we do, we wanted to learn a little bit more about you and your career path. So maybe, Pat, we could start with you. You know, we're curious where you're from and how did you become interested in sustainability science?
Thanks. So I originally come from Oregon, the west coast of the US, and I grew up outside of Portland, Oregon. And I grew up, I guess a funny anecdote is when I was a little kid, for I think my 4th grade birthday, whatever age that corresponds to, I told my mom, said, "What do you want to do for your birthday?" And I said, "Let's do a trash cleanup." And so for whatever that sort of shows, you know, I guess I think
it shows a lot.
I think it shows a lot, probably too much. But I've cared about doing things for the environment for a long time, you could say. So I got an undergrad degree in biology, took a few years off, went back to school, got a master's in water resources and hydrology, took another few years off, got a PhD in sustainability science from Stockholm University, and did lots of other stuff along the way.
So I'm his wife, right? So I'm allowed to butt in and tell him that.
Of course.
But when he says he took some years off, he didn't take years off.
What should I have said?
When you were a temp, you spent it like thinking about how to communicate climate change.
Yeah, I guess that's true.
And like, how do we make schematics and images that convey the importance of how our actions actually matter to the environment? This is not taking time off.
And I guess I started a consulting company. That's not taking time off.
That cared about the environment and how we did. So
okay. That's okay. That sounds, but I mean, if nothing else, it was a winding path. And I'm now lead scientist at the School of Global Environmental Sustainability at Colorado State University. And what that really means is I get to ask and answer questions about sustainability really broadly defined. So everything from trying to cook up things around machine learning and the Human Footprint Index, to thinking about sea level rise, to thinking about coming up with kind of radical visions of what the future might look like using storytelling techniques. So all sorts of things.
Very cool. Very cool. Yeah, we love hearing about winding career paths. I think there's a need to kind of normalize that, because a lot of young students coming up, they see these professors in these positions or people working for consulting firms, and it might appear that they have these linear paths, but yeah, there's definitely work to do to normalize that, I think. Yeah. So Libby, how about you? Where did you come from? Where did you grow up, and how did you get interested in what you're working on now?
Yeah, so my path is the stereotype. So I think it's really good when we talk about me and Pat together. And actually, Pat's he's useful for many things, but when I talk to my students, I like to constantly point to him as a great example of somebody who's very different to how they got to where they are than me. And I'm just one of many, right? So my background is in math and physics. And actually, I originally wanted to be a high energy particle like study hydrogen particle physics. I knew that since I watched the movie Contact at the age of 12, and Jodie Foster is amazing. I want to be her. My dad said, that's a physicist. And I was like, I don't know what that is, but that's the thing for me. And it wasn't until I did research in the area as an undergrad. One day there was a fire in the particle accelerator that I was at outside of Chicago at Fermilab, a tiny fire, it's tiny. But it suddenly dawned on me that all these people have spent a decade studying this one question about this particle called the neutrino, this almost massless particle. And they realized that if this tiny fire had been much worse, the entire project's done. And I remember that day as the day I said, whoa, I want to ask a ton of questions every single day. I don't want to devote my career to one question. And I think I got sort of lucky in realizing this is not the path for me. And so I realized I have to do something else. And unlike a lot of people that study climate, like Pat, who's been passionate about the earth, you know, for me, not that I don't care about the earth, I do care about the earth a lot. But honestly, the way I figured out what career I wanted to do is I said, I don't want to be bored. I want to ask questions all the time. What's really complicated? And I came up with the fact at the time that the Earth system was so complicated that I would never run out of questions. And if I got a little bit bored with, say, the atmosphere for you know, a few years, the ocean, the land surface, humans, volcanism, space, the sun, all of this was part of earth science and technically part of climate science. And so I was like, oh, I'm set for life. So once I figured that out, I went to graduate school at the University of Washington, got my PhD in atmospheric science. That's where I met Pat. We were both at University of Washington at the same time. And then I did a postdoc at Columbia, and now I'm faculty here at Colorado State in atmospheric science. So I did sort of more of that direct track. Whereas Pat, yes, has very much been winding. I like to say, though, Pat's the reason I remember there are humans on the planet and that they're involved in climate change. Because I'm very much about like numbers and like rocks, and anything with biology sort of grosses me out and is way too complicated for my brain. And he's the one that's like, well, remember, there are humans making these decisions. And I'm like, ah, yes, humans. So it's a good mix, I think.
Yeah, right. Yeah.
You're laughing because you know it's right.
Yeah.
You don't just double CO2 in a model and see what happens.
Yeah, let's just see what happens.
Where did it come from? Where does CO2 come from?
Right, right.
Let's hit it with 4 times CO2, and Pat will be like, that's terrifying. Just see, right? So anyway, okay.
Right.
And I wanted to ask one more question before we get into the content of this research you've been working on. But I was curious, so you're both living together, you know, you're a couple, you have a young child, and working through the pandemic. I was wondering if you could just quickly talk about your experience at home trying to navigate that remote world with a young little kid.
Well, we came up with a good system.
So we have 2. We have a 2-year-old and a 6-year-old.
Oh, okay.
So during peak lockdown, I guess last year for us, you know, after March, and everything, like
until this past month.
Yeah. We came up with a system where we would essentially have these like morning shifts and afternoon shifts or evening shifts. That really helped because we could just like toggle 100% one way or the other. And since we were both academics, we were very much in control of our own schedules. So we could really just say like, nope, can't meet then. These are my windows of time. And
like 5 a.m. to 12:30 and 12:30 to 7:30.
For a while, that's what we did. And then so when you're working, and when you're parenting. And honestly, there was a lot of like, it was very freeing to have that, because then when you're taking care of the kids, you are taking care of the kids, you know, and you go on walks. You don't go anywhere because it's a pandemic, but you can go outside places.
Yeah.
And that was nice. But then also as an advantage for this project, we could sort of like high five at the door, and then the other person could take over, continuing on whatever task we were trying to work on for this project. And so that was kind of fun. That was kind of cool.
So Pat makes it sound very rosy.
Yes.
When you ask this question, I have this deep dread and exhaustion, and I sort of feel like I have to lay down right now. So it was so hard. I will say from my perspective, it was so hard.
Yeah, it was. It was really tiring. Don't get me wrong.
But I think I will say this project we're going to talk about was honestly my therapy. Everybody's talked about like trying to, there's like no time for self-care the past year, like let alone even thinking about it. But for me, things, you know, for everybody have been so dark. And this project, you will see, like this project was the hardest thing I've ever done in terms of science. I didn't think I would be able to do it over and over. And I kept telling Pat, it's not going to work. I can't figure this out. And I think one of the reasons I did is I needed to shut that part of my brain off that dealt with emotions. And this project really let me become sort of a computer. And I had to think so deeply about numbers and about this machine learning technique that I was able to shut the rest of the world out. So for me, I really see this project as incredibly important to me, like mentally in surviving the past year, which is strange.
Wow.
That's amazing. Yeah. I love hearing about couples and people's mechanisms of how they're dealing with the home life and all that stuff. And it's everybody's got their own approach, but it sounds like you figured it out. And and congrats on this work. It's spectacular. And maybe that's a nice lead into getting into some of the details about it. So I'll pass it over to Karen.
Well, I'm just curious, actually, as a follow-up to Stu's question, is this a project that you already had kind of in mind pre-pandemic, or is it something that arose, you know, by being together, being stuck at home? And
well, so it came. So I have a colleague, the third author on this paper is at University of Michigan, Neil Carter, and so Neil was visiting Fort Collins to give a seminar at CSU. And we went out for lunch, and it was NASA had its annual Roses call, which is their omnibus funding call. And we said, hey, let's try and find something we can work together on and write a proposal. So we were talking about it, and we had an idea, and I told Libby about the idea, and she said, cool, not going to work.
It was real back and forth. It was just not.
It was an ill-posed question. But then Libby and I were talking about what machine learning can do.
This was after the pandemic started, though.
Was this after the pandemic?
Yeah, because I remember we scribbled, we were passing off kids, and you drew a quick picture.
Oh. And
that's right when it was like, okay, maybe we can do something now.
Yeah. Okay. And so we were coming up with this idea, and when we got to a point where it sort of passed, like this is something machine learning might be able to help with, sort of test. That's when we started working on this idea originally for a funding proposal.
Which was rejected, by the way.
Rejected, no big deal.
I know.
How dare they?
How dare they? Well, now I sort of feel like joke's on them. We did it anyway, and then I'm like, or are they sitting there going, "Well, haha, we gave them nothing, and they did it
still
anyway."
Did it anyway.
Right.
Either way, cool science happened, I guess. So that's a good thing. And so we really started with this approach, thinking in terms of a funding proposal. But we're starting to get into the science part, so I don't want to put the cart before the horse.
So maybe let's jump into it. So Stuart mentioned the Human Footprint Index. So maybe you can tell us a bit more about what that is, and how it was originally developed, and what it's used for.
Right. So the Human Footprint Index is something that's been around for decades, and it's this index of essentially human pressure on the global land surface. So you could almost think of it for every spot, on like a pixel basis, how much have humans impacted that place. And so like 100% would be like a highway going through Toronto or something like that, a big city. And then a 0 would be essentially like the wilderness somewhere. That's more like whatever untouched by people means, it would be that. And so it's this index of human pressure that captures sort of this gradient, and it captures lots of things. So the HFI, as it's usually made, is it's sort of a labor of love. It requires a lot of different kinds of data. You have to have data on roads, populations, kind of the built environment, agriculture, all sorts of things. Grazing, all sorts of things. So it takes in a ton of different kinds of data, and then it requires quality control, QA, QC, that sort of stuff, to make sure that the patterns that they produce from this kind of composite weighting process of the data produces a map that makes sense. And because of that, because it requires all this data, it usually lags the present day. So for the most part, these data sets tend to lag the present by around 6 or more years. And so right now, for the most part, if you were using one of these data sets, you would have data that's about 6 years old, give or take, and not counting the new one that we made. And so, but a problem that arises with this is what people use this for a lot of the time, this HFI data, is to look at how this interacts with ecology, with wildlife conservation, so species movement across the landscape. In fact, some people use the HFI actually as sort of like a resistance term in like a wildlife model. So wildlife are moving around, and if there's higher human footprint, well, that's harder to move against because there's lots of people there for whatever reason. And so if you're using older data, then maybe you're not getting the most up-to-date picture that you could. And of course, it's as good as was available, right? So that's the best that was available. And so one of the things that we wanted to try and see with this project is say, well, what if we could find a way to make a much more up-to-date, almost like a near-present human footprint index? Because for a lot of these, especially sustainability applications, conservation applications, a more current data set could help a lot.
Mm-hmm. And so in this paper, we've kind of talked about machine learning quite a bit in a bit of the introduction here. But so you've developed this new machine learning technique for predicting the HFI, and you use satellite imagery in order to train the model. So can you describe a little bit more about sort of the workings of this machine learning algorithm that you're using?
Can I take that one?
Yeah, why don't you go take that one?
Okay.
I think I could answer it, but I think you would answer it much better.
All right, let's see. Okay, yeah, so actually the way I described it to Pat is he's like, oh, I want to be able to predict this HFI thing everywhere. So what do I need? And the way I describe this is, it's really simple. You take a piece of paper and a pencil, and I actually told him you need to take a piece of paper and a pencil. And I want you to write on the left-hand side something you can get or see with your eye. And then a black box, just draw a box and say magic or machine learning, whatever you want to fill it in with.
I like magic.
Yeah, that's what I typically tell my students. And then the output is HFI. And the whole goal is if you can finish this picture and you can tell me that first bit, then I can do the rest. Maybe, we'll see. But you got to give me that first bit. And that was the hardest part is really communicating with each other who have different backgrounds. What does it mean, that input? What is it we're looking at? We finally, figured out, so Landsat imagery is just satellites looking down on the surface, right? This is something our human eyes can do. And I said, okay, if I were to give you an image of the Earth, could you give me an approximate value for how much humans are impacting? And he's like, yeah, I'd look for roads, I'd look for buildings, I'd look to see little cows or something in there, or fence lines for grazing, right? I'd look for whether it looks like it was a dense forest and trees were chopped down. And if I can see those with if you can see those with your eyes, then potentially machine learning can see it too. And so the whole concept is we teach this convolutional neural network to take these images and look for these things that mean humans are present, and then convert them into a single number. So a value from 0 to 1, where 1 means, as you said, it's like cement roads through a city, and a 0 meaning people really aren't there. And so the part I had to do was, we had to get all the data, which that's a different story. This was truly big data for me. And also we started with Indonesia, actually. So the whole project was just supposed to be for Indonesia, which is already pretty darn big, actually at this scale. And how do we teach this convolutional neural network to look for these human impacts? And the answer is we did, and it was able to identify them and turn them into this number. That was pretty.
And maybe just to jump in terms, just depending on everybody's familiarity with how this would work in terms of the machine learning side, it's we were utterly reliant on the fact that people had already made maps of the human footprint index. And so that was sort of I'm doing air quotes right now, truth. And so what this neural network would do is it would say, okay, well, I've got this satellite imagery, and you've told me that I need to guess 0 to 1. Okay, I'm just going to guess 0.4. All right, then it would check, did my prediction match what was on this actual truth data? And it was, at the beginning, wildly wrong. And so then over time, though, it was either rewarded or penalized with math to right? Is that?
It's fine.
Okay, good. To get better at answering that question, predicting a better value, so that eventually its accuracy was very good. The neural network's accuracy was very good, such that it could say, look at a satellite image and then accurately say, okay, that looks like now this, 0.67 or something. And that was actually very close now to what the truth was. And so without that original data, though, we couldn't have done this project.
Yeah.
So one technical question about the paper. I noticed that you wrote in the paper that you only used a relatively small amount of the data to train the model. And I was just wondering, how you decided kind of how much data to use, or how, was it related to, how close the answer was getting, or how did that process work?
Yeah, so great question. So we only train on 3% of the data we have. And machine learning is known to be data hungry. So you might think this is really silly. Why didn't you use all your data? A few answers. The first is I'm not a computer scientist and I didn't know what I was doing. So I had to learn a lot about how to really process big data. I was running it on a high performance computing system. It wasn't on my laptop or anything. But I realized that I could only really, I couldn't even open the amount of data I needed. The computer would explode, if you will, if you tried to open the files you needed to train this. So you actually had to open files, read the data you needed, and close the files, reopen the next file, read some of the data, close the file. That process is slow. So really you're getting this balance between memory issues on the HPC and my impatience. And I didn't want to wait more than 3 days to train a model, because I had to train 8 different, though also the way I had it set up, the memory would still max out with a certain number of files that I repeatedly opened and closed. And so what it meant was I didn't even train the whole globe at once. I actually have different sections of the globe I learned. And if each of those takes 3 days and I run it for 3 days to find that it didn't work very well, then I have to start over again. So you find that this is this balance between impatience, amount of memory, etc. So this is one of the reasons in the paper we try to sort of sell this as a first step. I have no doubt that software engineers out there can do this better and faster than I did. But ultimately what I did find, Karen, is that if I added a little bit more data, or even if I doubled it, my answer didn't astronomically improve. And actually the model was okay. It's pretty good the way it is. And we decided that rather than refining it for another year, let's get it out there so experts who really know what they're doing can maybe make it better.
Okay, cool.
I was looking through the paper, and one thing that jumped out was this. So at one point you mentioned the idea of the black box, so machine learning and this black box occurring. And you use this visualization technique called layer-wise relevance propagation, which I'd never heard of before. It sounds like Latin to me. So I was curious, if you could explain what that means, and is it a common approach now for trying to, understand what's going on in these black boxes, I guess?
Yeah, so this is where my research group is really going. There's a fancy acronym for this too, XAI, for Explainable AI. It sounds very fancy. And really what it means is let's not have it be a black box anymore. We should probably know how it's getting its answer. One of the reasons being, we don't want the right answer for the wrong reason. As scientists, that's terrifying, because our goal is to actually understand why we're getting what we're getting. But on top of that, you think about this paper where there could be policy implications. We don't want people making big decisions on data that's getting the right answer for the wrong reasons, or a method. So it turns out, so we use this method called layer-wise relevance propagation. However, even since writing this paper, since this is such an active area of research, my group is really exploring this, as is others, and finding there are so many other tools out there that are somewhat similar. And it's really exploded in the last, I'd say, 3 years or so. And part of this is because, as I said, this trust issue of should I trust what this method outputs? You've heard maybe the phrase garbage in, garbage out. So these methods will always output something, and it's up to the scientist or the user to decide if they should trust it or use it or not. And so I see these tools as a technique to help us make that decision. And what this method does is it says, okay, here's my guess of the human impact. How did you come to that guess? What parts of the Landsat imagery, what parts of the land surface did you look at and focus on to get your answer? And so in the paper, we show that, if a road goes in and the human footprint index goes up, did the neural network use that road in deciding what that value was? And we show some examples where we can use this layer-wise relevance propagation method to actually say, yeah, the network focused on the road, that's good. As humans, we can then understand that it came to the conclusion the way we might. But this is one of many applications. I will say one of the reasons I find interesting of why has this explainable AI exploded so much in the last few years, and I think a big one is the commercial and private sector has gone from doing things like predicting cats and dogs and horses and lamps and images, and started talking about things like self-driving cars, right? Where lives are at stake, and suddenly getting the right answer for the wrong reason is not just a silly mix-up or a whoops. I mean, this is a big deal. On top of that, governments are now requiring that if you're, say, a bank or an insurance company, you need to have proof from the beginning to end of the thought process you used or the method you used to get that particular quote. And if you can't explain it, you can't do it. And suddenly there is a lot of money going into the computer science community for explaining these, quote, black box methods.
So your new machine learning or ML HFI index is broadly consistent with the previous HFI estimates, but there are like a few differences. So I was wondering if you could describe maybe some of the differences and why you see them. What can you attribute these differences to?
Yeah, totally. So I always like to start off with like the things we did wrong, it does wrong, or like the limitations.
Or major fails.
Major fails,
yeah.
Get those out of the way. And we know systematically that for whatever reason, the CNN has a lot of trouble predicting the correct answer in essentially rocky deserts and some really mountainous areas. And it's not totally clear why that is. It could.
I have guesses.
Yeah, I know. Some of the guesses could be like shadows, right?
Really, it's wherever it looks like there's a road,
right.
But like the spine of a mountain covered in snow looks like a road.
It does, yeah.
Right, or something, or a fence line, and I can't figure out how to fix it.
But then there are also some strange features, like parts of Saudi Arabia show up as like very impacted by people, very high human footprint index, and there are parts of Saudi Arabia that do have significant human footprint, including just in the middle of the desert from oil exploration and stuff. So I think that with more training, especially in some of those deserts, we could get a CNN to get better answers in some of those places. And so that's the biggest divergence. But I will say that there are also parts of the world where I think that the machine learning approach actually came to a more accurate answer. So what I mean by that is there are parts of the world where the training data, the original data, had maybe really low human footprint, let's say in a part of Venezuela. But then if you go there and you look at it, you say, well, this is covered in agriculture. And then you look at the MLHFI, and the MLHFI says it has a higher human footprint that would correspond to agriculture, more or less. And so the fact that we only trained on 3% of the available data means that the CNN is now almost like equally predicting every single spot on the planet. There's no issue of like a data blind spot that maybe a more model produced or data intensive approach might have, where, oh, we don't have any data in that part of Alberta, so we're just going to have to go with maybe a lower number, or it's kind of we'll use the model to smooth that out. That's nothing. We have satellite imagery everywhere, and so as long as the CNN has been trained to predict at whatever metric we use to evaluate its performance, then it's going to do that everywhere on the planet and sort of equally well. So that is a little bit of an advantage in that sense, where if we trust the training, then it's going to do equally well across all of the satellite imagery. Would you agree with that?
Yeah.
Yeah. Okay. So I guess those would be the two ways that they differ. So it's either they agree, and they both got the answer right, and then there's the two where it's one got it right, the other got it wrong, and then they both got it wrong. I don't think there are very many where they both got it wrong, though. Actually, I spent a lot of time doing manual QC on a lot of this stuff, and by manual I mean using like a special joystick mouse to zoom in and out of Google Earth using the time-lapse feature and comparing and contrasting, like did the changes that the MLHFI approach actually bear out? Like, can we see big changes from, say, 2000 to 2019 roughly?
Spent many an evening after that. in and out.
You know what?
Yeah.
And honestly, I had a lot of fun doing that. I love looking at maps. This was like essentially you're like flying on this little joystick, like in Google Earth, like being like, let's get the right angle there. Like, what is this thing that I'm looking at? For the most part, it was really fun. There were a couple of places and things where it was really hard to actually figure out what the heck that landscape was. Yeah, so there's this in the middle of the island of Borneo. There was these really strange features that the MLHFI picked up. And then when I looked at the satellite imagery, I was like, I have no idea what this is. Like, I don't know if this is like some strange like salt marsh thing that has weird sedimentation or something. And it was these rings and everything.
And my worry was, this is our initial training. So I'm like, am I just out to lunch? Is this thing just wrong in this really important location? So,
and then it turns out, so then I went and I was on like Street View driving around trying to figure out like, what is this? Like looking at the actual kind of like horizontal landscape. And then I actually went to Google, I looked up news articles from the region and then used Google Translate and to figure out what's going on here. And it turns out it was just some artisanal mining, like small scale artisanal mining. And for whatever reason, the waste material were these little mounds that looked, I don't know, it looked like some other planet.
But it wasn't in the original HFI, which is why we were concerned.
Oh, right, yeah.
That's what was odd, is that this was one of our first examples of a place where the MLHFI saw something in imagery that the original HFI didn't clearly have paperwork for.
Right.
It existed.
And it was actually sort of like a first instance of saying like, oh, wow, we might pick up new things. Like we sort of thought like it would be great if we can just like do as good. I think there are certain features now where, because of, again, it's the satellite imagery is sort of like being interpreted everywhere, that it's we're potentially picking up new things, but it's just sometimes hard to then recognize every single kind of landscape. So
this is one thing where us working together has been really great, is my geography skills are lacking. And also, if you notice, just listening to Pat talk about these things, you have to know that what different countries and different areas and provinces, how they make their money, what people spend their time doing, and have this huge sort of global perspective on humanity and what they do to really understand, is that real or not? I don't even know what a mine, other than the ones I see around here, look like, and to know that, oh, I should look in this region, they are good at this and that. And so without that, I think I could have created a product, but I would have had no way to know if it made any sense or what it was we're looking at. Whereas Pat, given his winding path, career path, honestly, has spent so much time thinking about how humans interact with the environment and make money and produce goods, that he could look at these and within seconds know what was going on. So this is one of those cases where it was just like, wow, you need people with different perspectives working together sometimes.
Wow, so cool. So you mentioned like some of these differences that you saw and some potentially like new things that haven't been identified in the previous HFI yet, probably because it's just kind of, as you said, doesn't keep up to date, right? So what are some of the kind of the other sort of differences that you've seen, like in some parts of the world? In the map that you show in the paper, it looks like there's an increase in HFI, in other parts there's a decrease. So maybe you could kind of, I don't know if there's a way to generalize those results, but maybe I'll turn it over to you to describe those differences.
Well, yeah. So, wait, there's two different things. Like, what are the big processes that changed between 2019?
So a big thing is, because of this process that we have Landsat imagery in 2019. And this is why we got excited. Is now we can do the same thing for a year that has no HFI. It doesn't exist. Nobody's done it yet.
Right.
And we were actually able to use the same, if you will, magical black box that's maybe not so black anymore, maybe a little gray. And we can push our 2019 data through and treat it exactly the same way and get an updated MLHFI. So in that case, some of the changes or differences, Karen, in terms of time, is we can now say, what did the HFI look like in 2000? What does it look like in 2019? And let's take a difference and look at them. Is that what you're talking about?
Yes, exactly. Yeah.
So then we can start to say, now this is exciting. Now this is new. Nobody's done this before for these 2 years. Maybe you want to talk about some of the differences.
Yeah. So I think you actually can generalize a bit. And so there are parts of the world where things sort of just got more developed. So let's take a place like Slovenia. Okay, so in Slovenia, It's not a story of, oh, there was a brand new extensive mine that went in and that changed everything for Slovenia. No, it's roads got bigger, people built more houses, just like the general background processes of development. As any place grows, it's going to have more kind of human pressure just from expanding road networks, society, etc. So you could almost think of that almost like just like a gradient, a radial expansion sort of from every built surface in a way. And that was true. That's a story that's true of a lot of places on the planet. It's not necessarily surprising or exciting, but that's just, the slow creep. But there are places that changed very dramatically. So in the last 20 years, say, like palm oil plantations in parts of the world have just become extensive in a way that they really weren't 20 years ago. There was just a massive increase in palm plantations. And that's true in a lot of the tropical areas, particularly in Indonesia. And so you can see just, and maybe if you were zoomed out really far, you'd be like, it's green, same. But it's not, because you can see the road networks that go in between the palms, and you can see that it's, a plantation, this regular planting of palms. Other things are where you have road networks that are just going into relatively pristine rainforest or very low impacted rainforests in, say, South America, and just massive increase in road networks and mining. And so parts of the Guyana Shield, so Guyana and Suriname, they're just the gold mines and other mines, I should say, going in there have just expanded dramatically in the last 20 years. And so that's another big systematic change.
Just one fun one that I found, really fun, this one region in China, we thought something was wrong with my data, and in the end it was fine. They just built more land in the water.
Yeah.
So suddenly it used to be water. There used to be no human footprint, if you will. And then suddenly there's this big blob of dirt and
port facility.
And I got all nervous again. And Pat comes in and is like, no, look what happened. And you can watch as they built it from the Landsat imagery. Yeah. And again, the MLHFI picks this up because it doesn't care where the data came from.
Right.
Clearly, there is now a port there.
Yeah.
So.
And so there's that. So it's like mining, essentially like coastal reclamation to build new port infrastructure, the slow expansion of cities, and then agriculture is a huge one. So deforestation is like one side of that coin. And you see, like in the Amazon, there's something called like the herringbone pattern, the fishbone pattern, where you see this increase in the expansion, increase and expansion of deforested areas. And then sort of the counterpart of that is either ranching or agriculture is what usually replaces that forest. So those are really the biggest patterns. Honestly, though, the processes of decreases in MLHFI, those were fewer and harder to find. There were some, and there was
one was from a mudslide. It decreased. The HFI decrease that was on the west coast of South America. There one region where there was mudslides. So there used to be a town, and now there isn't. Wow. But that was one of the few places.
And there are a couple features also where we're sort of not sure, but we could be seeing like a signature of, I don't want to say a signature of sea level rise, but something like coastal erosion at least. And so there could be places that were more closely populated on a coastline, and now there's less coast there. And so there, the decreases are much more difficult to sort of generalize or understand because they were much rarer, for one thing, but also the processes are much less clear, like what's driving that change, that reduction. And so for some of those, I'm a little bit, I guess I'm more skeptical about the reduction side. Doesn't mean that it can't happen, obviously, like the mudslide is a perfect example. But like the voluntary reduction in human footprint in a place is not antithetical to human society, but it's approaching that.
That kind of connects to sort of the next question, I guess, about so throughout the paper you're drawing connections with this HFI index and the SDG, or Sustainable Development Goal 15, which is life on land. And so you do some analysis kind of looking at countries that report making progress on this particular SDG. But then your algorithm also shows at the same time that they have an increase in HFI. And I was wondering if you could talk a little bit about that contradiction and, how can both things be happening at the same time, or should we question, like, are they happening at the same time?
Yeah, I think it could be all of the above. But so like SDG progress, the way it's assessed, so the Sustainable Development Goals are 17 goals that were agreed upon, signed off on in 2017 or 2015. And with a goal of achieving all of this interrelated sustainable development progress by about 2030-ish. And so life on land is mostly about terrestrial biodiversity conservation in one form or another. So that could be protecting land, protecting intact forests, preventing land degradation, protecting endangered species, that kind of thing. And so different countries are going to achieve their sort of country-specific goals related to biodiversity conservation in different ways. So a place like Morocco might try and have different levels of governance than another country. And so they might have more capacity to say, you know, we've already got protected forests, now we're just going to increase enforcement and funding of those protected forests. And that's going to be one way that they're making progress toward their country-specific SDG targets. Whereas a country that is still trying to get a handle on the forest that it wants to protect, I don't want to single out a country there, but there are many countries that are trying to figure that out. And so they might be earlier in that sort of sequence of activities where they're going to say, we're going to try and figure out where we want to protect things. And just doing that is going to be progress towards our SDG goals. And so it's sort of, I don't like the idea necessarily of questioning the stated progress. It's just understanding that if the country wants to be making progress about protecting its lands, it has to at the same time acknowledge that its lands are changing. So even if we try and demarcate forests or we try and change enforcement of what those forests are, if those forests themselves are changing, that has to be part of the same story. And it could be that those two things coexist. And that would actually be kind of a good thing, understanding that, because people are going to still develop, like we're still going to need to, there are parts of the world that are still in dire poverty, and some of those places need to develop in a way that allows those people to have like a more actualized existence. So we can't say like, sorry, you can't do that because you're not going to achieve SDG 15. But at the same time, understanding how some countries can navigate that, that tension of saying we are going to need to develop, but we also need to try and steward our lands in a way that's going to be not just like good for wilderness, but good for people, good for the environment is important. Not sure if that answers the question, but that's sort of, it's a complicated situation. In the paper, we try and dive in a bit into 3 specific case studies to just tease out a little bit, what are the policies in these different kinds of countries? And I think we look at Morocco, the Gambia, and Guyana specifically.
As a follow-up to that, do you think, so this type of machine learning application, do you think carrying forward that will serve to improve transparency and monitoring for sustainable development goals kind of going forward?
I mean, maybe. It really depends, because data is only good as the people that want to use it and the people that can use it and the people that are resourced to use it. So a big challenge is that countries are very differently resourced and there's different technical capabilities to use some of this stuff. And so if it just falls down to say NASA or some other, space agency or big data agency, Google, it doesn't matter that it's freely available. It doesn't matter that anyone can access it via the internet. It's only as good as the people that are actually going to be able to use it. And so if you don't have anyone in your country's government that can do something with Google or FinGen, it doesn't matter that it's freely available, right? So I hope that it can become more widely available, but that's going to require a lot more concerted effort and capacity building. The stuff that's hard because it requires talking to people and getting people to sit down and talk with one another and agree and learn. That's like the hard part. I'm not sorry. I don't mean to diminish the hours and hours that you spend training a convolutional neural network to, but I think that an equally challenging part,
no, definitely worse,
is getting people to use this stuff and learn how to use it and make it better.
And I will add to that. I think another hurdle from the data side is what I brought up before, which is trusting it.
Yeah, trusting it.
Is it getting the right answer for the right reasons? We spent 10 minutes telling you all the ways it screws up. We didn't, right? So suddenly now we're going to say, oh yeah, I can be wrong, but still go make really important decisions for your entire country's population. So I think it's complicated on how you incorporate this. And I think, at least the way, again, I describe it to my students, is this is one bit of evidence that should be included into your big pot of lots of evidence when you make decisions. And so maybe it will be used as one of 20 or 30 or 40 things when in thinking about what to do, but that you then get into the world Pat's discussing, which is it's hard even if you do have that data.
Right.
Yeah,
Right.
yeah.
Yeah.
So you identified a few potential hurdles there to its proliferation, I guess. But conversely, what do you see, like what gets you most excited about the future of these kinds of approaches for environmental science broadly?
I think mine, yeah, Pat's will be better, but this is my perspective. I am motivated as a scientist, not for specific results. So not what's going on in the Gambia or whatever, but I am motivated as a scientist to change how people think broadly, sort of the teach a man to fish, teach a person to fish kind of approach. And so to me, what I'm most excited about this is it says you can use data we already have to address problems and use machine learning to get insight into maybe processes you thought you couldn't, or you couldn't do it at a global scale, right? We did this on the entire globe. And so I get excited about that. And actually I got an email last week after the paper came out from someone who said, just this morning, I was on this big panel making policy decisions. And her point at this panel was, we need to get more creative with how we use data to support policy and see if it's being met. We need new ways of using the data we have, the Earth observing systems we have. And this paper came out and she's like, I was able to point to it and say, we don't have to do it this way, but here's an example of how people are getting creative. And so when I hear that, I sort of feel like, boxes checked. I did what I set out to do kind of thing. So that to me is already, to me, I'm excited. We've already sort of done what I wanted to do. So with that said, now you can take a more nuanced approach.
That's not what I was saying.
Go for it.
Okay, so I think that another side of this is, there's going to be a flood of new data products, new data tools in the coming years, decade, whatever. There already is, but it will become more so, just as like computing power goes up. I think a lot of these machine learning tools are going to drive significant innovation in the way and the kinds of data that we have available for whatever, informing decision making, or you name it. I think a big challenge though is going to be, how do we make sense of this flood of information and create kind of useful information, not just data, but information, knowledge, etc. And that's a lot harder. That's not easy to do. And also the other side is, how do we get people to use it? And so part of me thinks that there's a huge scope for kind of interdisciplinary work around this, to where are people, how do people access data and information right now? And how can we connect the conversation around that with this sort of revolution a little bit in the availability of some of these new insights? As an example that might be not totally on point, but maybe, is sort of this like gamification of how people interact with information, and how can we get people to be thinking about, say, biodiversity conservation, but in a way that's incorporable into their daily life. So even if you're a government official, I'm not talking about the average person on the street. Maybe they don't need to be terribly concerned with biodiversity conservation, but the government official who maybe lacks certain capacity needs to be brought in or part of this conversation. So is there a way to sort of turn these things into apps, turn these things into forms that are consumable, usable by people? And that's still an area that is growing, but probably needs to grow a bit faster to continue to provide this bridge between these communities.
Both great answers.
Thanks.
Yeah, and it kind of like makes me start thinking about, citizen science, kind of validation of your HFI index, and all these kind of cool ways to engage with the broader public through having these, data products out there. It's kind of exciting to think about.
Yeah, in a way that would be amazing. Imagine an app where you just you check in and be like, you rate. You don't even have to like, is this like the wisdom of the mob? I know there's a word for a fancier phrase for that, but you have to rate 0 to 1. How impacted is this place? And so maybe there's like this emergent sense of what do you mean?
Sorry, I'm just laughing. Like you go to a restaurant and it's like 4 to 5 stars. Also, I give it an HF 5.8.
Imagine that's like the new, we get Google to put that right under the star rating.
Yes.
is the HFI rating. We would have so much data.
Where people live.
Where people live, exactly, true.
Yeah, of course, yeah. It would be definitely a biased citizen science campaign, but
I mean, but there would be enough. There's so many different ideas I like the citizen science thing you mentioned. Like, imagine being able to kind of crowdsource people's maybe open access kind of Creative Commons photographs, and then come up with a photographic metric that then you can sort of validate or cross-reference HFI data. And that would include places that are maybe fewer data points, but some data points that are in areas that are scarcely trod, the Sierra Nevada or something like that. In California, you would still get some data because people are out there hiking. Anyway.
So just to kind of wrap up, I guess you mentioned, Pat, the value of kind of doing this interdisciplinary work, and these words like interdisciplinary and transdisciplinary are really kind of buzzwords in academia and encouraged by funding agencies and all these kinds of things. But obviously, like case in point, your paper, it can yield like really incredible, rewarding results. But of course, we also know that it can be challenging. And so I'm just wondering, we kind of alluded to it a bit throughout the conversation, but overall, how was your experience collaborating together on this project from a kind of interdisciplinary perspective, rather than kind of a married couple perspective?
Good. Thank you for distinguishing that.
Yeah, so I will say, so first these words like transdisciplinary, interdisciplinary, every time I say them and then I tell Pat what I think they mean, he sort of rolls his eyes. It's like, that's not what they mean. So I think there's like, it's so confusing what this even means. Not that I want to go to a dictionary, but all it means to me is like working with people that speak different language and somehow trying to get something out of it in the end, right? And I think in this scenario, this I think was the most positive, productive, easy one of these projects I've ever done. And I think part of it was because I hate the word grew organically, but this is what it is. It came out of the need. He doesn't do machine learning, didn't even know how it worked. I mean, now we can talk about it. It sounds like he coded the whole thing himself. Like, it's amazing how much you can learn about each other. I now know where some countries are, but but it came from the need, and both of us having our own piece of the puzzle that fit together, but we couldn't do it without the other. I couldn't do, quality control without him, and he didn't know how to set up this convolutional neural network. So that part was awesome to me. It was like so easy. Whereas in the past, when I've done these sorts of projects, often they're forced upon us sort of by funding agencies, for example. It's really hard when it feels like you're sitting around a table with experts in their own field, just saying, let's come up with a project that uses all of us, go. And so to me, this was awesome. I felt like I had a role. I knew what everybody else's role was. Neil's role was a big important one. I will point out that there was a third author here. One of his big roles was a sanity check for Pat, because I can get really excited about what's being output, and Pat could get really excited, and I could get him excited. But then we give it to Neil after a few weeks and say, like, is this like total crap? Or is this good? And if he got excited, then we knew we were onto something. And so, yeah, I thought it was great, but unfortunately, I don't think it normally is. It hasn't been like this for me in the past.
Yeah, and I think part of it, I think it's good to say that it wasn't imposed from the outset. It sort of emerged. Like the collaboration was again. I also like it just grew. Like it emerged. I think that I'm a little bit bitter because I'm an interdisciplinary scientist, and I keep trying to get pitching cross-cutting interdisciplinary work, and funding agencies, as much as they say they want it, a lot of the time they don't. And I think a big challenge is that maybe it's generational. It could be generational, but this idea where they're mandated to fund, or the people are asking for interdisciplinary work, yet sort of a lot of the gatekeepers are still very disciplinary, hyper-disciplinary. So if I've published many papers where I would get reviews back that were essentially the reviewers arguing with each other because they weren't, because they didn't know what the other said. You'd have a social scientist arguing for things to be rigorous in a social science way, but not commenting on any of the, say, physical science aspects or something like that. Even those distinctions are a little arbitrary. And then the physical scientist would be doing the same thing, but in the other direction. And I think there's a challenge here because interdisciplinary science as a field needs to figure this out. Like, how is it gonna exist in this world that still sort of demands disciplinary rigor?
Or depth. You should always be rigorous.
You should always be rigorous, fair. But I mean, this idea of disciplinary purity, perhaps even sometimes. And that's not, if you're saying you want interdisciplinary science, it's not going to be pure in that sense. It's going to, you have to be, there's a give and a take, a push and a pull, and it can still be very rigorous. And you can still get, obviously, like with this paper, we got really cool interdisciplinary results asking these questions. But I still think that it's a little bit of an uphill battle.
But let's take our paper. This is a great example. All right, let's think about the disciplines represented. Computer science. The computer scientist reviewed this. They'd be like, what was this Barnes lady thinking? Why did she set her CNN up like that? Why did she only use 3%? Didn't she know that if she'd used Amazon's blah, 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 cloud computing, that she could have done? I mean, it would have been endless of all the things I could have done differently or I did wrong. But not wrong. I mean, ultimately, I produced the right thing. I could have done better. That's what I have to say. Okay. As a computer science, they would have said, oh, people train on satellite imagery all the time to predict things. There's nothing new here. This paper would never have been published even close by a computer scientist. It's not computer science. Okay. Then we go to the HFI committee and they're going to be like, we have an HFI. Yeah. Okay. You updated a little bit, but it's not good in places. How can you possibly sell us this, this product when you know it's wrong in places? So you start to look at it from that perspective and you're like, yeah, how did this get published? Right? So, and yet I truly do believe this was a useful paper for the community, even if each community on its own is going to see flaws. So I feel for Pat. I am very much not typically in this interdisciplinary role. And so I see that sort of struggle and frustration that everybody wants this word, but doesn't really know what they're asking for.
And but I will say that I think it's changing. I think like if we had the same conversation 10 years ago, 20 years ago, people would be like, oh my gosh, it's changed so much. Like NSF has these mandates now, et cetera, et cetera. So I think we're in the middle of a shift, but I think that shift is not, some people are not going quietly into the night and yielding this disciplinary purity when it comes to interdisciplinary work.
Yeah, that's interesting. So in the review process for this particular study, how did you find that? Did you feel like it was interdisciplinary or?
I did actually.
Oh, I did.
Oh, you didn't?
Really?
What did you think?
It just seems like a bunch of conservation people.
Yeah, that's true. Well, we could preference certain reviewers. I should say that it was rejected from.
Oh yeah, we sent it to like, where did we send it?
I mean, we sent it to like Nature and a couple other like.
But their point was
journals.
People are already doing it. Like people already use machine learning with satellite imagery. So what is new? There already is an HFI. So what is new? Fair. I mean, fair point.
Yeah.
We have no issue with that. I get it. But yeah, I think I felt like it was mostly the sort of conservation. So the users of the HFI, which honestly is probably good.
Yeah.
They're the ones that would actually use this data. And so if they don't like it, but as you can imagine, something that since I publish a lot of machine learning these days, I have written what a neural network is so many times, right? Because if the people in the disciplines are like, I don't know what this is, you need to act as though I've never heard of it before and describe it from scratch. Where at some point, it's like, I don't have to go into the mathematics of linear regression every time I draw a line, thank goodness. Or every paper would be so long. We don't actually have to describe every climate model in an appendix every time we want to use their data. But right now we're still in this world where machine learning is only just really coming into the earth sciences, that people want that. So the review process here was really reviewers from my perspective, my side, reviewers saying, You need to, in essence, teach me machine learning 101, 102, 103 before I even start to think about what you've produced, which I understand. On the other hand, at some point, it will be a waste of time to actually have to have every author repeat what this is every paper. And I don't know where that line is, but we're not there yet. Clearly.
Interesting.
I see what you mean. And it's like, who gets to decide that, right? And I'm not sure.
The reviewers, I guess. But I think the editor was supportive.
So maybe just to kind of wrap up, maybe you can speak a little bit, Pat, about kind of the importance of this type of interdisciplinary research, specifically for the SDGs and, sustainability type of research. I know like at the University of Toronto, this has been kind of a big theme in the last year or so, trying to bring people across, disciplines to work on these 17 goals. And so maybe as a sustainability science expert, you could kind of speak to that.
Yeah, I mean, that's a big question. So this idea of sustainable development, I'm going to try and not get too philosophical here. Libby's shaking her head. No philosophical answers right now. But I think this is a huge challenge. And so the world is trying to simultaneously foster or steward development in a way that is ethical, just, responsible for all of these people around the world, and systems, not just people, but systems themselves, by a deadline that's 9 years away from today. Are we going to achieve every SDG by 2030 in every place? Absolutely not. There's no way. Should we keep trying? Of course, we should keep trying. And at the same time, there's new energy to really start to address carbon emissions and climate change very seriously, hopefully very seriously. And I think there's a lot of people looking with a lot of optimism to the COP, the Conference of Parties in Glasgow at the end of the year. And so I think that the need for people to open up their minds and work with others to try and collaboratively solve these questions around sustainable development, very broadly defined, I think it's the most urgent thing that we can do, because it's going to require almost everything that we can do. It's going to require these radical changes in society, and that don't have to be painful, but they will be big. Like hopefully we're all going to be doing things very differently 20 years from now to meet that goal. And so, but we're not going to get there if people aren't thinking with an interdisciplinary mindset that the world's challenges require thinking that is certainly going to include stuff from outside what you learned in college. And so if the more people that can recognize that, and the faster they can recognize that, the sooner they'll be starting to look for those people to work with, right? And so I think that that's a shift that I hope starts to accelerate, and that we see more projects like this, where there's there's an appetite for doing this, and a desire to work with other people that aren't an expert in what you do.
Yeah, and I'm going to add, this goes a little with our funding, but thinking more broadly, the funding discussion, but thinking a bit more broadly. I think so I'm going to speak as one of these scientists that's supposed to be coming together and wanting to do all this interdisciplinary work. I think we need to, as fields, as science, we have to value creativity more. Okay. I think a lot of reasons we stop some of these projects is it's not perfect for all of these disciplines. We're not going to get it through every gatekeeper, and so we stop. The only reason we even were able to do this project is the two main leads lived together and could talk about it, and realize that even if it never got published, we actually had fun and learned from each other. Most of the times we don't have that luxury. I wouldn't have gone through this with the uncertainty of will this ever turn into anything if I didn't actually, like, honestly, I think if he had just been a normal collaborator, I probably would have given up at some point, wondering what's the point? Should I spent many hours of my life on this project, so should I really be doing that? And I think we have to be allowed to be creative and not have the solution every project, every paper. We have to, quote, be able to, succeed 20%, but maybe there's a nugget there that some other group then takes it the next 80% or even only 60. And that's why I want to repeat, I think this project was fun and good for interdisciplinary science because it actually wasn't the answer. I do not think our specific version 1 product should be used necessarily for policy. but I do think someone else can now take it the next step. And so I just wanted to say, I think creativity is slowly dying, and I think we need to bring it back and be allowed to fail.
Yeah, that comes from also almost saying like, it's a buzz phrase to say high risk, high reward, but it's, I think what I mean though, is that it's okay, like, especially when the stakes are getting higher with some science, we ought to feel like we can, especially like in this safe space of doing some science, we should take some risks and try things a different way. And this is a good example of trying to answer a question a different way and taking a risk. And we could have totally failed.
Well, yeah, I didn't think it was going to work.
Yeah, you really didn't think it was going to work.
No.
And so I think that we should be a little bit more like celebrate creativity and also try and be adventurous with the science that we're doing.
Yeah. I think this paper, it does read like an adventure. It's this world tour, you highlight all these places and all these fancy things, and you've been able to speak to the ground truthing aspect, like maybe not literally, but virtually going to the ground in these spaces. And it sounds like an adventure to me. So congrats again.
Thank you.
Yeah. Thanks so much for joining us.
Absolutely.
Yeah.
Whenever I get to talk about this stuff, I realize this was fun. Thanks for getting us a chance to just like, you have to sit here and listen. You're a captive audience here, but I guess that's what podcasts are, right? People can always stop or pause or whatever.
Yeah. Well, and speaking of going beyond disciplines, part of doing this podcast for Stu and I is to have these conversations across disciplines and learn and share what we talk about with our audience. So
Absolutely.
That's super fun. Thank you.
Thank you both.
All right. Thanks.